Sorry about that. So anyway, well, I missed that part. But that's okay. So anyway, so as I was saying, graph traversals, you visit every vertex, and then the two classic ones are the depth first and the breadth first traversals. And anyone here who's taken CS classes, they probably know this and maybe are having some twinges of pangs of anxiety. And actually, and this example shows acyclic graphs, but these ideas can be applied to regular graphs. And this is kind of an important idea in terms of algorithms. I kind of threw this slide in here because we're going to look at a bunch of ideas that sort of relate to traversals, and I kind of wanted to just draw this distinction of traversals. And actually, on that note, I didn't know what to call this, so I'm calling them graph perambulations, which are really, I kind of like that word, are really this idea of walks, trails, paths, circuits, and cycles, which we'll look at what they are. I've seen variations on the nomenclature. I think that my nomenclature here matches to what Wikipedia has, so it must be correct. And essentially, this idea is really types of travels on connected graphs. And so the example is our metro again. You could think about you're traveling on the metro is really one of these things, and we'll look at these a little bit here. So I took Euler's Euler's original publication and defiled it in the paint program. And so essentially, if you take your walk from C here and you go down to A, B, come back up here, it's essentially doing this. You're coming C to A to B, back up to A to C to D to A. And of course, we failed to end up where we started, and I'll show you why that's the case in a minute. But essentially, a walk is essentially where you give these sort of it's a vertex and edge. It's basically you list vertices and edges in this fashion. And if a walk can be called closed if the start vertex and the end vertex are equal. And we'll see those in a sec here. So actually, I'm not going to walk through these examples just in the interest of time, but I'm going to put these, as I mentioned before, these slides will be up there so you can sort of walk through and see how these, I think these give good examples of how these structures work. But I have this little diagram. I believe this is actually called an Eulerian diagram. Actually, it was pointed out to me, I think earlier, I think I said I mixed Euler and Königsberg up when I was giving that example. So Euler's the mathematician and Königsberg is the city. And since I'm recording this, I wanted to make that correction. So if I actually said that, I both feel foolish, but I also now I have a correction. So this diagram is kind of nice. So walks is sort of, you can have really anything. You can do any collection of vertex edge. There's no restrictions. Trails, you don't repeat any edges, and then paths, you don't repeat any vertices. Now, if you close these, if you close a trail, it's called a circuit, and if you close a path, it's called a cycle. And actually, cycles are also fall into circuits, which also fall into trails. I actually don't know if this is a true Eulerian diagram because I don't know if you can do that duplication there. So anyway, there's two famous examples. There's the Eulerian trail and the Eulerian circuit. The Eulerian circuit was actually what Euler was trying to do on the 7 bridges of Königsberg. And essentially, the heuristic is incredibly easy. All the vertices have to be even in order to be able to do that. Or if it's a directed graph, you have to have equal in and out degrees, which kind of makes sense if you think about it. And you can immediately see that all the vertices are odd here, so you can tell immediately that, hey, I can't do that. The Hamiltonian path, the closed path, the Hamiltonian cycle, are actually a little bit more complicated. They're actually visiting each vertex exactly once. The Hamiltonian cycle is actually a special case of what's known as the traveling salesman program, where all your distances are 1. And this is actually, I believe, an NP-hard problem, with the exception of these two graphs and others like it, which are what are called 3 regular or cubic polyhedral graphs. This is our tetrahedron or dodecahedron, and I believe that you can automatically say those guys actually have Hamiltonian cycles. So anyway, so I want to talk about the idea of subgraphs, and this is actually pretty important. This is actually one of the sort of seminal areas of graph theory study. and actually has a lot of applications in sort of real world analysis and like social networking, network theory and stuff like that. Since, I actually talked earlier about the idea of, I kind of blew through that slide on sets, and I'm actually not going to try to revisit that, but in theory, since you can have sets, since you can define graphs in terms of sets, you can define graphs in terms of subsets, but there's an easier way to think about it. You can actually think about just deleting edges and vertices. So you take a graph and you just remove them. And then one important note is that whenever you remove a vertex, all the edges connected to go away because you can't have any dangling edges. Essentially, here's just a simple example which actually illuminates this principle, I think, pretty nicely. Here's our graph G, and so we're going to remove this EJ right here. So boom, that's a subgraph. Pretty easy concept, pretty intuitive, which is nice because I remember looking at this in one of the textbooks, and it was described not so visually, and it seemed to be very hard to understand some of these ideas when they're really easy. This one, we're going to remove this vertex here. So we take this away, and now we've got that vertex would have been here, and all these 5 edges go away. And this is an important note too, is that your subgraph is actually contains 3 connected components. So your subgraph may not, a subgraph of a connected graph may not be connected. We'll look a little bit more about some of that stuff. 2 subgraphs that you see a lot, and we're going to talk a little bit more about spans in a sec. The first is a spanning subgraph, and what that means is that you're just deleting edges. You have all your original vertices. So this guy right here, again, just a real simple edge deletion, and this is a spanning subgraph. Actually, the previous example of the edge deletion was also a spanning subgraph. And then the other one is called an induced subgraph, or also can be called a vertex-induced subgraph. And what that means is you just take a subset of vertices of the original graph. So we're going to take this one, and this one, and form this triangle. And then you get rid of all the edges that aren't connected between those 3 vertices, or the subset of vertices that you take from the original graph. The idea of spanning actually extends to the idea of trees. So what you can do is you can take a graph, and then you can put an acyclic graph or a tree on top of that graph, take the original vertices and then put edges where you have edges, and you can come up with this idea of spanning trees. And there's actually some really interesting things about spanning trees. So essentially these 2 are examples of spanning trees. There's the idea of a minimum spanning tree, which is actually on weighted graphs, where you take a graph and you actually find all the spanning trees, and then you find the one where you sum up all the edge weights, and that's a minimum spanning tree. And you can actually have multiple minimum spanning trees per graph potentially. So it doesn't mean one, it might mean a set of more than one. There's some interesting ways to compute spanning trees. One's called Cayley's theorem. It's this formula here. It actually applies to our complete graphs here. So this is actually K2, K3, and K4. If you plug this formula in, you get 1 for K2, which is pretty obvious. You get 3 for K3, and then you get 16 for K4. And then there's actually another. We'll look at another thing a little bit later called Kirchhoff's theorem, and actually called also the matrix tree theorem, which actually shows you other ways to calculate spanning trees on the other graphs other than the complete graph, because clearly it's probably a more interesting problem. Another area of subgraphs is the idea of cliques. A clique is actually, and I think this actually might come from social networking or sociology concepts, because a clique has social connotations. But a clique is essentially the idea of a complete subgraph contained within a graph. So in this example, we've got our cliques of K3, which are the 2 dark blue ones, or I'm sorry, K4 rather, which are the 2 dark blue ones, this guy here. And then we've got the light blue ones, which are K3. And so you can essentially think about identifying. Clearly, you could have others. And the other thing, too, a little other side note is actually technically K4 actually has 3 K3s in it, so just, but they're not really shown. Again, sort of a Neo4J graph theory idea. So some of the ideas we just looked at. Your cipher queries return subgraphs. So essentially what you're doing is when you're querying, I guess potentially you can return the entire graph, but that's probably not what you want. and probably not very efficient. So essentially what you're usually looking at is you're trying to deal with the idea of subgraphs within a graph. Neo actually has something separate from Cypher called the traversal API, which can be accessed, I guess, through Java, maybe can you do through Rust too? Or,
yeah.
And through Rust as well. And you can actually do traversals through a graph, or presumably as maybe a subgraph within the graph. And that actually has depth first and breadth first options that you can set. The traversal API can also return either paths or subgraphs. I think the subgraph feature is called the expander feature, and that's, again, something that you can set in the API. So graph coloring, I feel that this needs to be talked about just because it's sort of such a critical area of graph theory. It's actually sort of a variation on the labeling idea, where you're labeling a graph with colors. But the rule, actually, but you can label both vertices and edges, but usually you're just doing doing vertices rather. And the idea is whenever you color something, the two adjacent ones cannot have the same color. So there's actually a whole bunch. I mean, this is actually a whole area of graph theory. It actually gets into sort of combinatorics as well. So the edge coloring is actually not very interesting. Essentially, what it's saying is that if you take a graph and whatever degree has the max, or whatever vertex has the maximum degree, your coloring, or it's actually called the chromatic index, is the smallest edge coloring. So what you're looking at is the smallest colorings on these things. But in this case, it's pretty straightforward. You're either getting the maximum degree or the maximum degree plus 1 of the graph. The maximum degree being, if you took all the vertices and found that the highest degree, that would give you your edge coloring. So it's not terribly interesting. But I put it up there just sort of for context. The chromatic numbers actually comes up a lot more, and it's actually a more complicated problem. And then I just threw in a few examples here. These are some of the graphs that we looked at earlier. Your complete graph, the chromatic number is always the n. So kn, this is k6, so its chromatic number is 6. Star graph is always 2. Your wheel graphs are 4 for even, 3 for odd. And then your cycle graphs are 2 for even and 3 for odd. But I guess probably the most interesting thing about coloring, the graph coloring, is actually the four-color theorem, which is a pretty famous theorem. It was actually the first major mathematical theorem proved by computers back in the 1970s. And this is actually the problem that they started back in like the 1850s. De Morgan and Francis Guthrie, I think it was. And actually, the interesting thing, so the idea is it's actually about map coloring, about not having contiguous regions, not having adjacent regions colored, and it actually relates to the idea of the dual graph concept. So anyway, so what we've looked at so far is we've looked at various properties of graphs, or a few properties of graphs, things like genus and chromatic number and chromatic index, which are actually sometimes called invariants because they won't change no matter how you draw the graph. And this is where it sort of starts to get interesting, and sort of there's the interesting applications, is that you can start using these properties to look at your data and look at how graphs are structured to find out more about them. And we'll look at a few properties, and we'll look at how that works. So a couple of simple properties is the order of a graph is the number of vertices, pretty simple. The size of the graph is the number of edges. The girth of the graph is the length of the shortest cycle contained in the graph. And so here's our Peterson graph again, and our order is 10, our size is 10, and our girth is 5, meaning you can't get a cycle that's smaller than 5 in that graph. I threw in a couple others. We'll look a little bit at the idea of the spectrum. This is actually the eigenvalues of the adjacency matrix, which we'll look at shortly here. But you also have these polynomial ideas. The characteristic polynomial, again, is related to the adjacency matrix. It's related to these guys here. And then this chromatic polynomial. I threw these in here because the idea is that you can also have not necessarily individual numbers describing graphs, but these more complex sort of mathematical structures. And a couple others, as we looked at previously, a vertex has a degree measure, and again, it can, for acyclic graphs, or rather directed graphs, it can have an inbound and outbound. There's a concept of distance. It's also called graph geodesic distance, and basically it's the number of edges between the shortest path. So in this graph, if we take these two vertices here, there's a distance of 2. You could also go this way, 1, 2, 3, but that wouldn't be the shortest path. So the shortest path here is there. And then again, in weighted graphs, these ideas come up again, but you would actually be counting the weights. So if you went along here, I think that comes up to 70. And that's an important idea if you have weighted graphs, because weighted graphs definitely come to play a lot. All right, so this is a little bit harder concept. It's the eccentricity. And essentially what it is, it's the longest, shortest path to another vertex. So if you start from here, your longest shortest path is 5, meaning that you could get. I guess in this graph, I mean in theory, yeah, I guess in this graph you can't really get a. I mean, this isn't the greatest example because there's not like a longer one to show, but it's a little bit. I guess the concept's a little bit confusing, but it's basically the furthest you can go to get to another vertex. So from wherever you are in the graph, the furthest point in that graph is the eccentricity. The center of the graph is based on the eccentricity concept. So actually this graph is labeled with all the each vertex has its eccentricity labeled there. And so the center of the graph is the set of graphs with the smallest eccentricity. So that's 3. And it kind of does, have that sort of central feel to it. And we're going to look at centrality here in a sec. And the centrality is actually a very important concept, especially in emerging graph analysis and network analysis. And then here's centrality, for example. And there's actually like a lot of different centrality measures. And I actually took these off of Wikipedia, and I just included these 2 because I think they have like 6 of them there. So the between this centrality, and again, I don't want to get too heavy. Like I said, these slides will be available so people can pursue these on their own, these ideas on their own, and I've got some references at the end too. So the idea between the centrality is the number of times a node acts as a bridge along the shortest path between 2 other nodes. And this is between the centrality, and you can see it's kind of red to blue. So red, I think, are the more central ones. And you can see in this measure, the thing to kind of look at here is that in this measure you're getting sort of a different set, and down here this is actually what's known as eigenvector centrality, which is actually what PageRank technically is. It's a measure of the influence of a node in a network, and you can see here in this centrality measure you're getting sort of a different set of vertices, and this actually comes up in like sort of network analysis and social network analysis in terms of like finding out who our influences are. But there are many different ways to do this. So if you're pursuing this, expect to be looking at a lot of different things. So there's this concept of a radius and a diameter. The radius is the minimum eccentricity of any vertex. So what you do is you essentially calculate the eccentricities of all the vertices, and then you take the minimum number. And in this case, your radius is 2. So the eccentricity, as I mentioned, is the shortest or the longest shortest path to any other one. So you're calculating all of them, and then you're saying, okay, it's 2. And sort of conversely, the diameter is the maximum eccentricity of any vertex. So your maximum eccentricities are 4. So your diameter of your graph is 4. And here's some mathematical notation describing those concepts. Density, actually, this is actually somewhat of an intuitive property. Again, we're talking about simple graphs here, so single edges between vertices. And this is our n-1 formula, or n-1 triangular number formula that gives you the number of edges. And so this is your complete graph, and this is actually a graph called an empty graph. I didn't get into this concept, but these 2 graphs are actually what are known as complements of each other. And this actually has a density of 0, which I think kind of makes sense. And this has a density of 1, which is the maximum number of connections you can have on a simple graph. And so you can see your density formula here is actually essentially an inversion of this formula. And so again, measuring on simple graphs. Another metric is click number, and this is things that people look for in graphs. What is your maximum click that you can find? So that it's the maximum complete graph within a graph. And these things are nice thing about some of these concepts is they're unlike the eccentricity related ones. These are fairly intuitive. All right, so network analysis. This is obviously a huge field now, especially. And actually, I think I clipped this out of, well, essentially what you do is, so it's essentially, I guess, considered to be a subdiscipline of graph theory. So just replace the word graph with network. And actually, I clipped this piece out of Wikipedia, and I actually didn't even know like how this applies to statistical physics or particle physics. The rest of them kind of make sense a little bit. I think originally this stuff got started, and a lot of these things, a lot of these like network analysis things got their start in like sociology, like back, like the 50s and 70s and stuff. So network analysis I actually got some, like I said, I have some references later on this. So, but essentially, there's sort of three things in network analysis that you're interested in. You're interested in the individual nodes. So your idea of the centrality of nodes, or link analysis, so like page rank, or you're interested in groups, which is your subgraph, and we'll look at some other aspects of subgraphs in network analysis. Things like clicks, and so in subgraphs. So you're looking at how things group, or like who are groups of friends or terrorist cells and that kind of stuff. And then also the idea of the entire properties of the entire network. So some of those like graph properties that we looked at, but usually probably more along the lines of why can I not say that? Statistical distribution of nodes. I think I need more beer. So this is actually I included this in here. It's the power law distribution, and essentially, this is actually the formula for it. But it actually pretty much is in social networks. Actually, this is fairly common. Like things like Justin Bieber has way more followers than exponentially more followers than probably everyone in this room. And then whereas more famous people like the guy and CEOs of like Neo would have maybe be working their way up that exponential curve. Orders of magnitude more than us normal folks, assuming there's not anyone famous in here. So the idea of network analysis, so this idea of clustering, and again, as I mentioned, the clicks are an important idea, but you're also looking for dense subgraphs in your entire network, and those generally those generally indicate certain things that you're looking for. Like I said, groups of friends or terrorists, or I'm sure there's many other examples. And this is kind of a nice example. There's actually kind of a hierarchical. You can actually also have hierarchical structures to these as well. And so essentially, if you look at this actually has almost sort of a self-similar fractal pattern in the way that the person. I sort of stole this from someone. I'm not sure who. But you can see that you get sort of like 5 sections, and each section sort of has a sort of similarity at the top level. But what you're really looking at here is first of all, you got this hierarchy where you've got this one, you got at one level you've got these 5, but then within each of the 5 you've got 5 more little ones. And what you're looking at is the density of the connections between the individual nodes versus the connections within versus the outside connections. So you have a higher density in your clusters than you do between the clusters and other nodes. So that's I guess it's the intra-cluster density versus the inter-cluster sparsity. I'm sure that clears it right up, right? So another thing in network analysis is the idea of flow. And so this actually is used a lot in engineering, like operational research, and actually electricity, fluids, traffic, and ecological systems. And essentially it's the idea of how things flow through a network. What's the transportation networks? What's the most efficient way to get stuff through a network? Or how in general are things flowing through a network? There's actually, I guess I didn't realize this, that there's this whole area called matching problems, including which is the idea of assigning things, or there's a famous problem called the stable marriage problem. and I did not realize that until I was doing this, that we're putting this talk together, that's actually, I guess, a sub discipline of this network flow concept, which doesn't seem terribly intuitive to me. I'm still not sure how that fits in there. So another interesting and perhaps more intuitive idea is the idea of robustness. And this is important if you're building a network like a computer network or the internet around the world, is how robust is your network and where are the vulnerabilities? And then that actually gets into some ideas of there's these ideas of cutting, where you can, it's sort of similar to the subgraph concept, where you're removing vertices and edges. This is actually a bridge is where you can remove an edge and end up with two separate connected components. So if you remove these two red ones, you get three separate connected components. So a bridge is like, if I remove that one edge, I break the network into two parts, or I break the graph into two parts. Similar, you can have the idea of a vertex, which is called a cut point. Again, cut point, if you remove this individual vertex here, you've now separated these two pieces. And these things, they can show you vulnerabilities. If this was like some kind of communications network, and you could identify that this is a vulnerable node and you need to add more redundancy. It also can show you bottlenecks that, okay, well, everything that needs to get from here to here needs to go through this node. So again, these are bottleneck problems in the network. There's a thing called a Cheeger constant, or an isoperimetric number, and those are actually measures that allow you to calculate these things. I'm not going to get into those, but I'm just mentioning them. Algorithms, huge area, and I could probably do, or I don't know if I could, but someone could probably do a whole talk on, on algorithms alone. Essentially graph algorithms are just algorithms you apply to graphs. Some of them are about determining properties of graphs. Some of them are about finding elements or subcomponents within graphs. As we mentioned, traversals. Also finding walks in graphs, and then there's actually some applications of linear algebra that do some of these things. And there's actually quite a few sort of problems that have a high degree of computational complexity, or like our NP hard problems, like our traveling salesman problem. So one fairly common and well-known algorithm is topological sort, and that's the idea where you're listing vertices such that you're listing subsequent dependencies. And this can be used for job scheduling, or tasks based on their dependencies. And then that I give you the complexity here. It's the O of n notation. So it's the size of the vertices plus the size of the edges. And in this example, I give you all this, so we're not going to go through that. But if you want to come back and revisit this when I publish the slides, you can. Minimum spanning trees, again, another very common and commonly used algorithm. They're both, these are two, one's called prim and another's called Krustal. They're both greedy algorithms. And then they give you the computational complexity. There's some issues with how this stuff's implemented, how you implement your data structures to store the data, and how you implement your graph. We'll look at adjacency lists here in a sec. And then shortest path is a huge one. I mean, probably Dijkstra's algorithm is probably known to many people, hopefully. And there's a number of variation. There's a number of other algorithms that do shortest path. Bellman-Ford allows you to have negative edge weights. The A star is, I think, a more generalized algorithm. I actually don't know that much about it. And then there's Floyd-Warshall, which actually solves the pairs of like all shortest paths, and that actually is things that you might want to do in terms of like centrality measures, like find all the shortest paths through a graph and then analyze that data set. And then there's a couple others here. Essentially, I think there's a couple. I'm just sort of listing these out. There's algorithms for network flow. I mean, these are all things that you would use algorithms to find. Cycle detection, the shortest cycle. There's one called union find that allows you to find connected components, dense component discovery, and clustering. All right, so representation. Essentially, if you're going to work with graphs, you're storing them, and I'm actually not sure exactly how Neo does it. I guess I should probably know that. But we won't get into that. Maybe in the future we'll add that to this talk if it gets done again. So essentially, there's three common things that you find when you're looking at stuff. You have the adjacency list structure. And then you've got two tabular structures. One is the adjacency matrix, which we're going to look at in more detail here in a sec. And that's where you're just listing all the vertices as a table, so it's always a square matrix. And then you're just, for simple graphs like this, you're just dropping ones into where there are edges. This is called the incidence matrix, and this is basically you list all the vertices and you list all the edges, and then you put ones where they connect. And this actually gets into sort of now the idea of where you actually can manipulate these matrices. You can represent your graph in a matrix, and then you can actually start manipulating these and looking at things. And there's actually, when I was researching this, there's actually quite a few different types of matrices that you can have for graphs. So we just saw the adjacency one, and we saw the incidence matrix as well. There's actually this concept of a degree matrix where you just list all the degrees of each vertice down the diagonal. And then there's a distance matrix where you can list all the edges and you're listing the distance between each edge. And then there's these two called the Laplacian and the signless Laplacian, which we'll look at a little bit. I'll show you what those are in a sec here. Actually, I'll show you this right now. And all these things can be defined sort of conditionally. So your adjacency matrix, you're just saying if the I and the j have an edge there, then there's a 1. Otherwise, it's a 0. Your incidence matrix, if j connects to I, it's 1. Otherwise, 0. Distance matrix, if I equals j, you put the distance in. Otherwise, 0. I'm sorry, this is degree matrix. This is distance matrix, where you're just putting the distance of everything in there. And then these Laplacians actually end up being a combination of the degree matrix and the adjacency matrix. And actually, this is kind of interesting. So essentially, these matrices actually have these relations. The incidence matrix actually, if you multiply it by its transpose, you get this signless Laplacian matrix. And I know these come up a lot, and I know it's kind of a lot to look at, but trust me, if you get into this stuff, these things actually are fairly interesting and fairly relevant, and hopefully will make the Laplacian seem a little more relevant in a second. So a couple of things about matrices, specifically the adjacency matrix. The structure of the matrix actually, this is what I mentioned before, where you actually have the matrix where some of these properties like an undirected graph, for example, will have a symmetric matrix. So an undirected graph will have these two values will be the same. These two, essentially, you can flip it along this diagonal here as a symmetric matrix. So if you can flip the matrix over around that diagonal, and it's the same, it's called a symmetric matrix. So undirected graphs are always symmetric, and that actually has important properties when you start doing some of these matrix calculations. In terms of how the eigenvectors come out and eigenvalues. But we're not going to get into all that. Undirected graphs actually would not be symmetric. Directed graphs are not symmetric. I think I need to fix that. Yeah, that's okay. These are the last slides I did, so they're the roughest, I guess. So simple graphs always have ones, but multi-graphs would actually have the number of edges. Loops, if you had loops on your edges, you'd actually have values in here on the adjacency matrix. And if you were dealing with a weighted graph, you'd actually just put the weights in instead of 1. So if you can think of an unweighted graph as a weighted graph where all the values are 1. Actually, this is really cool in my opinion. So if you take the adjacency matrix and you multiply it by itself, in other words, raise it to multiple powers, you actually get the number of walks for that power. So if you go so for example here, A to B here, for example, which is 1, there's one walk of length 2 to B, and that's go down here and come up here. And that's actually, I think that's really cool. So if you ever want to calculate walks on a graph, you just you just raise the adjacency matrix to the power that you want. Actually, I think you can get away with actually not doing the whole matrix. I think there's some shortcuts if you're just looking at individual edges. But that's actually, I don't know, I think it's a really cool property of the adjacency matrix. Another really cool property of the matrices are that you can calculate the spanning trees from them. And this is our Laplacian matrix again. And actually there's two ways you can do it. You can calculate the eigenvectors. This is called Kirchhoff's theorem, where you calculate the eigenvectors and you multiply the n-1 eigenvalues together, rather, which gives you 20. Or you can actually take the Laplacian and you delete one row and one column, which is this guy right here, and you take the determinant of that and you get 20. And I actually ran this through like an online calculator, so if I got the matrix right, it's right. But it's actually really cool, the fact that you can do it. The other thing too, from I've seen actually mentioning that the number of spanning trees can be looked at as like a robustness measure of your network, which kind of makes sense. The more spanning trees you have, the more robust your network probably is. All right, well that's it. So any questions? And thanks for listening. And also references. I'm going to put these slides up. So there's a lot of nice free references out there. There's a bunch of stuff on Wikipedia. I have a couple of very expensive Springer books on here if you're so inclined to spend a lot of money. But there's a lot of free stuff out there too. So I suggest starting with that, and then or just and this guy actually has a nice little free book on graph theory. So yeah. Thanks a lot.